Well, that's kind of ugly. And it's precise, but kind of a mess to plug things into. So let's see if we can make some approximations. So let's write this again. We have area of the disk, Q over A, 2 epsilon 0, 1 minus Z over square root R squared plus Z squared. So here is our, I'm going to draw my disk sort of edge on here. So I'm looking, this isn't a rod, this is actually sort of a edge on view of a disk. Positively charged disk, we'll say. And here's the radius, so it's capital R. And what if we want to find the electric field at a location where Z is very close? So the approximation that Z is much less than R. Okay? Well, Z is much less than R. R squared plus Z squared is approximately just going to be R squared. Okay. Square root of R squared is just going to give me R, right? So I can write an approximate formula. Electric field of a disk is equal to Q over A over 2 epsilon 0, 1 minus Z over R. Okay? So that's a lot more simple. And often the case, we are looking at situations where we're very close to a charged disk, and so it might be more useful to us as well. And in fact, if you're really close, if Z is much, 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 much less than R, what does Z over R become? 0, right? So we might even be able to get away with just saying the electric field of a disk is Q over A over 2 epsilon 0. And that's really simple. And it also kind of gives a better sense of what the electric field looks like when we are that close to the disk. We essentially have a situation where if we're close enough, we're not getting too far away, the field just depends on the charge, depends on the area, and it's got a constant down here. This epsilon 0 is equal to 8.85 times 10 to the minus 12 in units of coulombs squared over Newton meters squared. So it's just a fundamental constant, the charge of the disk and the area. There's no dependence on the distance away. So provided I'm close enough, the field essentially looks uniform. We have the same magnitude here as maybe just slightly further away, the same magnitude there. And it's also fairly good approximation over the entire, or not the entire, but a lot of the area of the disk, okay? And much like with the case of the rod, it's only when you start to get toward the edge that the approximation breaks down. You start to get effects that look like that. So the field looks uniform, both in magnitude and in direction when you're close to the center part of the electric field of a disk. And that's kind of a useful thing to know. If we want to create a uniform field, then maybe having a electric or uniformly charged disk would be the most useful thing to have. Okay. Questions? So, bunch more derivation, but it just gives us a nice result that we can pull out of our pocket when we see a situation like this. Yes, but you will have to understand when they're useful, okay, and what approximations go into them. Okay, so you don't want to use, if you're at a situation where you have, like, if you have a rod and you are, very far away, you don't want to use the 1 over R formula. But if you're close enough, you might be able to use that formula. In similar situation here, right? Other questions? Okay, there's a special case that we want to take a look at. I just spoke about creating uniform field. And in practice, there's a specific situation that comes up a lot in technical applications where you have one disk that is positively charged, so we'll call this plus Q. And again, this is an edge-on view of a disk. And another disk that is same dimensions, and it's parallel to it, right next to it, but it has the opposite charge. So this is negatively charged. And there's a name for this device. Anybody know it? This is a capacitor. Okay, a capacitor is the simplest capacitor is just two metal plates side by side, and then you connect them, as we'll see later in the semester how you can actually, the mechanism behind charging a capacitor. But basically, if you connect it to a battery, you can drive current onto the capacitor, and charge builds up on either side. So you have what's called a parallel plate capacitor, specifically. Okay. Two disks, opposite, same magnitude of charge on each side, but oppositely signed charges. And so we look at the electric field at various locations here. If we want to look inside the disk, say at an observation location in the gap in between them, the electric field due to the positively charged disk is pointing what way? Pointing that way, right? So that's E of the positive charged disk. The electric field of the negatively charged disk is pointing the same direction, right? Because it's pointing towards the negative. If this distance, we'll call this distance S, which is just the gap in between the two plates. If this distance S is small compared to the radius of the disk, we're not too far away from either plate, how do the magnitudes compare? They should be equal, right? They should be equal because we should be able to use, if we're very close to the disk, we should be able to use this formula as our approximation. Electric field of disk, magnitude of the electric field of a disk is Q divided by the area over 2 epsilon 0. There's no dependence on the distance, okay? So it doesn't matter where we are inside this capacitor as long as we're fairly near the center part. Again, if you get toward the edge, the approximation breaks down. But if we're here, or if we're here, or if we're here, or if we're here, the magnitude of the electric field of the positive plate should be uniform. The magnitude of the electric field of the negative plate should be uniform. And so when we add those two together, we know they're in the same direction, so we can say that the net electric field inside the gap would be equal to, in fact, let's write it as a vector. We're going to have Q over A over 2 epsilon naught, 0, 0 for the positively charged plate. And we're going to have Q over A over 2 epsilon naught, 0, 0 for the negatively charged plate. You say, well, what happened to the sign here? It isn't one positively charged, it isn't one negatively charged. Well, you got to be a little bit careful because, again, we're talking about a magnitude here. So that really is a magnitude. And so, as usual, I'm just looking at the physical situation to figure out what the direction of this vector should be. So the magnitude of the field is the same for both, but it's pointing in the positive x direction for E positive, and it's pointing in the positive x direction for the field of the negatively charged plate as well. So when I add those two together, I get Q over A over epsilon 0. So that's another useful result. Inside a parallel plate capacitor, the magnitude of the electric field is just the magnitude of the charge on one plate divided by the area of one plate divided by the constant. Okay? So it's important here to realize this Q is the charge of one plate. The total charge of the capacitor is what? if I add those two charges together, I'd get 2Q. One's positive, one's negative. So the net charge is actually 0, right? So there's no net charge on a capacitor, so it's just a separation of charge. So the Q here is not the net charge, it's the charge of one plate, okay? Okay. So a capacitor is very useful. Well, it has a number of uses, and we'll see those as we go through the semester. It's useful technologically as for storing charge and storing energy, which can be used later on. But it's also useful for creating situations where we have a uniform electric field, okay? Because everywhere, almost everywhere, inside this gap, provided it's a small gap compared to the radius of the plates, we get an effectively uniform electric field, okay? How close to the edge? Depends on how good of an approximation you want, okay? I mean, technically, you move even a smallest away from the center, and this, is not, strictly speaking, true anymore, right? So it depends. I can't really give a stronger answer than that. For our purposes, we're often going to be looking at situations where we just want to get the basic idea, and so we can often make this approximation. Okay. Yes? Well, what's inside this gap? What's here? What's at this location? Nothing. Yeah, there's nothing here. Okay, so where is the charge? The charge is on the plates. Okay, the charge is on the plates. Well, the question we're asking is, what is the electric field made by those charge distributions at locations inside the gap? Okay. Now, maybe I didn't answer your question, so ask it again. Oh, inside the capacitor itself, as in like here, like inside. Oh, okay. So what I did was, all right. So I'm applying superposition. I have a positively charged disk and a negatively charged disk, and I already worked out what the field is due to a single disk when I'm close to the disk. Okay. So I've got an observation location in here that is close to disk number 1. So let's write it out maybe in stages. I have the net field. The net field would have to be the electric field due to disk number 1 plus the electric field due to disk number 2. Or I'll write it this way, the positively charged disk and the negatively charged disk, right? We're just applying superposition. So I say, okay, what's the electric field due to that positively charged disk? Well, I know how to deal with that. Superposition says I ignore the presence of the negatively charged disk. Just think about the positively charged disk. I know its direction is in the positive x direction, and I know its magnitude is Q over A over 2 epsilon 0. Okay? So I have a vector then that is Q over A over 2 epsilon 0 in the positive x direction. All right? I do the same for the negatively charged disk. If I ignore the positively charged disk and focus on what's the field due to the negatively charged disk, well, it's pointing in that direction, pointing towards the negative charge, and it's got the same magnitude because it's got the same magnitude of charge, it's got the same area, and there's no distance dependence here. If we're close enough to that disk, that's all that matters. Okay, so I know then that it's the same formula. I have another factor of Q over A over 2 epsilon 0, and then 0 in the y and z directions. Add these two together, and I'm just going to get, if I add 1/2 of something plus 1/2 of something, I can just get this back, right? So all I'm doing is adding two fields together. Okay. Okay. Questions?